Next, we'll be looking at a special case of the mean value theorem, and that special case is called Rolle's theorem. So as a special case, the first two hypotheses are the exact same as the ones that we had for mean value theorem. So we have that f is continuous on the closed interval, AB, and we have that f is differentiable on the open interval AB, where we don't include the endpoints. Okay? So when we are talking about a special case, we're saying in addition to the hypotheses that are met already for the mean value theorem, we have an added hypothesis. And so this third one here is our new hypothesis. And that new hypothesis is that if you plug in the endpoints, each one you're going to get 0. So f of a equals 0 and f of b equals 0. And so that's the extra new hypothesis. And when we add in that extra hypothesis, the conclusion statement starts out the same way. There is at least one C. And that C is in the same place. It's in the open interval AB, so the C is between A and B on the number line, such that. And here is our more specific conclusion equation. We have f prime of c is now not equal to the difference quotient that we saw, but rather something much more simple. It's just 0. But of course, this conclusion statement ought to be related to the mean value theorem since we're talking about just a special case. So let's see how that relationship happens. So for Rolle's theorem, let me remind you that we had an extra hypothesis. And that extra hypothesis was that when you plug in the endpoints of A and B, you get 0. Okay, so given that extra piece of information, let's compare the conclusions. So we've got the conclusion of the mean value theorem was that we remember the slope of the tangent line equals the slope of the secant line. So we have the slope of the tangent line is our f prime of c, and that equals our slope of our secant line, which was f of b minus f of a over b minus a. And then the conclusion over here for the special case for Rolle's theorem was more simplistic. We had f prime of c, so the same left-hand side, but instead on the right-hand side we just had 0. Now this isn't magic. The extra hypotheses really dictate that 0 without having to really remember a different separate thing. Because if we had, for the case whenever f of a equals f of b equals 0, well, what we end up having is, and that again is the extra hypothesis, this difference quotient f of b minus f of a over b minus a. What we get when we make that substitution is a 0 minus 0 over b minus a. We still don't know what b and a are. We know that they're not the same value, so the denominator is not 0, but we're looking at a 0 over 0 situation here, or sorry, a 0 minus 0 situation on the top, so we've just got 0 minus something we know to be non-zero, or over something we know to be non-zero. So the 0 over the non-zero value b minus a is simply 0. And so we can get from the mean value theorem conclusion statement to the conclusion statement for Rolle's theorem, just not by memorizing something new, but just simply plugging in the extra equations there from the hypothesis. So now the extra thing that I wanted to point out that's applicable for both the mean value theorem and Rolle's theorem is we had this extra idea that C is not unique. Because it says there exists a C, there's at least one C. It doesn't say there can't be more than one C, it's just saying that there's at least one C. And so in particular, let's say we restricted our interval there to be AB. Notice that this would satisfy the hypothesis for both mean value theorem and Rolle's theorem. Because we're talking about f of a and f of b being equal to 0 because those are roots. But then if we're looking at this nice, smooth, continuous differentiable function here, we have two different places where we have the derivative equal to 0. And those are wrapping back to our idea of local maxes and mins and critical points. They actually happen to be there. The local max and the local min. So there would be C1 and C2. So we see that there are two places in the interval AB that satisfy the conclusion there of the special case Rolle's theorem, since all the hypotheses for Rolle's theorem are met.